Today we're going to be talking about how to find sums of infinite geometric series. Now you might be saying, well, how can you find the sum of something that is infinite? We're going to talk about that in a minute and what that would look like. But some terminology, the sum S of n of the first n terms of an infinite series is called a partial sum. And in a way, we found partial sums above in the previous problem in the previous days. If we look back up here, we found the sum from 1 to 13. But if this was from 1 to infinity, then a partial sum would have been from 1 to 13. And that would have been a partial sum of the whole sum if this said infinity. So a lot of the things that we did the other day will come back to play here. The partial sums of infinite geometric or neither series may approach a value, but arithmetic ones do not approach a value. Meaning that, if you have an arithmetic sequence and you keep adding something to it, the value is going to get either larger forever or smaller forever. So to show this, let's consider these two examples here. So consider the infinite arithmetic series 2, 4, 6, 8, 10, and so on. Describes what happens to the partial sums for S of n if n is 1, 2, 3, 4, and 5 as it increases. So S of 1 would just be the sum of the first term, or 2. S of 2 would be the sum of the first two terms, 2 plus 4, which is 6. S of 3 would be the sum of the first three terms, which is going to give us 12. S of 4 will be 2 plus 4 plus 6 plus 8. And that's going to give us 20. And then S of 5, 2 plus 4 plus 6 plus 8 plus 10 is 30. So these partial sums right here that I highlighted in yellow, they keep getting larger. They keep getting larger, showing that the partial sums of infinite arithmetic sequences don't approach a value. Now let's look at this infinite geometric sequence. And you know it's geometric because you have 1/2, 1/4, 1/8, 1 over 16, 1 over 32. Our denominator is being multiplied by 2. Or you can say that we're multiplying each value, the previous value, by 1/2, making this a geometric sequence. And over here, what we've done is to kind of look and see, all right, if we just have the first term, adding that up, we get 0.5. We add up the second, the two terms, we get 0.75. Add up the three terms, we get 0.88. Add up the first four terms, we get 0.94. Add up the first 5 terms, we get 0.96. Well, we see that the value that these sums are approaching a value, and it seems like it's approaching 1. S of n seems to approach the number 1 as n increases. Oops. Okay. Now let's see if that holds up. Maybe once you find S of 6 and S of 7, it crosses 1. So 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32. The next term would be 1 over 64. So in my calculator, I'm going to do 1 divided by 2 plus 1 divided by 4 plus 1 divided by 8. And you could write these as fractions instead. The reason I'm not is because I want my answer to be a decimal, since all the other partial sums are decimals. So you see we get 0.984. Now S of 7, or the sum of the first 7 terms, will be all of these 7 terms. Okay, so whoops, we missed 8. And we're also going to add at the end plus 1 over 128. So in my calculator, I'm just going to go up and grab this, and I can do 1 over 128. So we get 0.99. Again, closer and closer to 1, but it's never going to actually equal 1. The sum is going to get closer and closer to 1, but never equal 1. So it's like an asymptote when we were talking about exponential functions. And you may be sitting there thinking, well, if I keep adding stuff to this, eventually it is going to be bigger than 1. Well, the fraction that we're adding each time becomes smaller and smaller. If we were going to go further, we would be adding 1 over 256. And then we'd be adding 1 over 512. And we can do that just to see what we'll get. Okay, it's 0.996 plus 1 divided by 512. Okay, so we're getting close, but again, as we're going close, as we're going to the next term and next term, what we're adding is becoming smaller and smaller. So that is why these infinite geometric sequences, these series, can approach a value even though we're always going to add something to it. So the value that the partial sum approaches is called the sum of the infinite geometric series. So this would be called, the sum of this infinite series would be 1, because that's the value we are approaching. The sum can be calculated as long as the common ratio has an absolute value that is less than 1. So if your R value is a fraction that is smaller than 1, then that means we could have a sum, an actual value of that infinite series. Infinite arithmetic series have no sum because of what we talked about up here. To find out the sum, the infinite sum, we would use this formula, and I'm going to be giving you that formula as well. And again, that's only true if the absolute value of the R value, our rate, our common ratio, is less than 1. If the absolute value of R is bigger than 1, then the series has no sum. All right, so on the next page here, we're going to follow these steps to find the sums of these infinite geometric series, if it's possible. So if we look at this one here, the R value is 0.8. And since 0.8 is less than 1, we can calculate the partial sum. Okay, so then what do we need? We need the first value, a sub 1, and we need the R value. Okay, the R value is 0.8. A sub 1 is going to be what we get when we plug in 1. 0.8 raised to the 1 minus 1 power, which is 0.8 to the 0 power, and that equals 1. So a sub 1 is 1, the R value is 0.8. So now we're going to use this formula. S is equal to a sub 1, which we calculated as 1, over 1 minus R. And R is 0.8. So we type that into the calculator. And we get 5. So as we keep adding the values of this series, plugging in 1, plugging in 2, plugging in 3, eventually, and we start adding all those together, eventually we're going to be approaching the number 5. All right, now in this one, notice that the signs are alternating. We have 1, then negative 3 over 4, then positive 9 over 16, then negative 27 over 64. That is a clue that the R value is negative because that's the thing we're multiplying each time. To figure out the R value, remember you can divide two adjacent terms. So I'm going to divide 19 over 16 by negative 3 over 4. So in the calculator, alpha y equals, and then alpha y equals again to do 9 over 16 over negative 3 over 4. So the R value is negative 3 over 4. And a sub 1, that is our first term here, which is 1. So now the infinite sum is going to be equal to a sub 1, which is 1, over 1 minus the rate. Well, the rate is negative 3 over 4. So now in the calculator, 1 over 1 minus, and then our rate, negative 3 over 4. And that gives us positive 4 over 7. So this infinite sum is 4 over 7. Now, letter C, I noticed that the R value, that rate right here, is bigger than 1. So there is no sum. There is no infinite sum for this one. All right, I want you to try these 3 problems below. Pause the video, give this a try, and once you're done, unpause it, and we can see what you got, and you can check your work with mine. All right, so here are the answers. So the first 2 were hopefully not too difficult. You got 2 over 3 for that first one because your R value is negative 1/2, and a sub 1 would be 1. For the second one, this pair problem, your rate is 3 over 2, so that means there's no sum. And then for the last one, you may have needed to figure out the R value with this work right here to get 1/4. And then your first value is 3 this time, not 1 like in the other problems. So when you plug it into the formula, you get 4. All right, these last examples are word problems. A person is given 1 push on a swing. On the first swing, the person travels a distance of 4 feet. On each successive swing, the person travels 75% of the previous swing. 75%, this is a rate of 0.75. What is the total distance the person swings? So they start off at 4, which is your a sub 1, and our R is 0.75. So as they're swinging, each time they go is going to be less and less and less and less until they eventually stop, and we can add up all of that distance. So the sum, or the total distance, is going to be an infinite sum where a sub 1 is 4 over 1 minus 0.75. And if we type that into the calculator, you're going to get 16 feet as the total distance. because they started off with 4, and they travel 75% of that, so it was less than 4, and then 75% of that, which would be even smaller, and eventually it would approach 16 feet. Now instead, suppose a person travels 3 feet on the swing. Okay, well, our ace of 1 is now 3. So that distance is going to be 3 over 1 minus 0.75. And when we type that in the calculator, we get 12. 12 feet. And that should make sense. You think about if you go on a swing and you suddenly stop kicking your legs, you're still swinging back and forth, but it's going to become less and less until you eventually stop. Now, the last problem here, we have a pendulum that travels, is released and travels 18 inches on the first swing. So that is your ace of 1. On each successive swing, the pendulum travels 80%, okay, R equals 0.80 of the previous swing. What is the total distance that the pendulum travels? So total distance, that's going to be ace of 1, which is 18, over 1 minus 0.8. And we type that into the calculator, and that's going to give us 90 inches. So that is it for sums of infinite geometric series. That formula is something that you're going to have to know how to use. I'll give you the formula, but it is something that you need your R value and you need your ace of 1 in order to calculate this. So thanks for watching. Make sure to like the video and subscribe.